Can I see those hands again, people who already know Rust? Oh, you're gonna be super bored. Oh man, okay, all right. Hands up if you know C++, and keep them up. And now, keep them up if you use C++ 14, or 2014, I guess. Okay, just curious. I mostly asked that because I wrote my first Lambda today for this talk for C++ 14. Okay, yeah, the abstract for this talk got sort of, I had to revise it. So I'm sorry if I sold you a bill of goods about WASM and stuff because I didn't have time to implement that as part of my talk. If you have your cell phones, the way I do my talks is all the slides are already online. You can take your cell phone now and take a picture of the bit.ly link at the bottom here. And you may want to because there's links to code as we go. And so if you care to visit the code yourself and go to the playground, you'll be able to do so. So a few more seconds. While I'm on this slide, I tried to compress my talk when I made this, which means I got rid of stuff that I usually always include, like what is Mozilla and why is Mozilla working on Rust. So while I'm on this slide, I work for Mozilla. I'm a research engineer at Mozilla, and Mozilla makes the Firefox web browser. But I know nothing about web development. I found the previous talk fascinating because I know nothing about that sort of stuff. And even though I have to hack with CSS just to make these slides. And Mozilla is doing Rust because it's now has Rust in the Firefox web browser. We're using it to basically make Firefox perform even better and be able to hack faster on Firefox without having to run into C++ issues, which if you're a C++ fan, maybe it has no issues, but we'll talk about that. So what is Rust? Rust is it's a new programming language. We're actually still in our 1.x release, but I think we're going to just be on 1.x forever and ever. It's been out for about 3 years now. We're going to have the 2018 edition out by the end of this year, which is sort of a big deal. But it's more than that. It's got this whole ecosystem with these websites devoted to deploying code and libraries that use Rust, and a whole community that we've built up to welcome people in. And this community is made up of people who come from C++, people who've come from Python, people who've come from Ruby. There's a whole bunch of people all coming together to make this melting pot for this language. It's emphasizing control over your code, being able to get low-level control over all the details, and emphasizing speed, but also emphasizing safety in terms of ensuring that your code doesn't have segmentation faults, but also ensuring that it doesn't have data races. So we care a lot about concurrency. We care about performance, and thus we care about concurrency a heck of a lot, but we also care about safety for concurrent code. And the big point here is that we want to be able to give you the ability to do low-level hacking without having to worry about segmentation faults and without having to worry about data races. And our simple slogan here is hack without fear. So why should you use Rust? Well, as I said, the biggest reasons, I sort of gave you this big outline before, but the biggest reasons in my head are safety and parallelism. No segmentation faults, no undefined behavior, no data races. Basically, if you stick to the part of Rust where if you don't type the word unsafe in ever, then you should be fine and you'll never hit any three of these top three bullets. But the other thing it enables is various kinds of parallelism. We are a multi-paradigm language that enables all kinds of parallelism. And we'll talk a little bit about some of those in this talk. But this is a performance meetup, and so I thought I'd jump straight into performance issues with a demo that if a lot of you have seen my previous talks, you've probably seen this demo already. This top part is Rust code. This bottom part is C++ code. They're pretty similar, actually, at least for something this small and simple. All this function is doing is adding all of the even numbers within a given integer range. And it's doing it with a simple for loop, and it's just looking at each one saying, are you even, by doing a modulo with 2. And if it's even, then it just adds it to an accumulated value and then returns it. Why did I do this function this way and not just a simple for loop? Because I found that the compiler always reduced it to a closed form solution when I used a for loop that didn't filter out the odd numbers. So that's why we're using this very strange function here. OK, now let's jump into parallelism, because that's what I want to benchmark here in terms of performance. So here's some code that's perhaps parallel. And it's perhaps implemented in Rust. I've included the link to the playpen. So Rust has this online playpen. So even if you don't have Rust installed yourself, you can go to this playpen and then go ahead and run the code. But I'm not going to do that because that would give away the punchline. So instead, this is the code here. And what it's doing is it's going to create a collection of threads in a vector. And then it's going to keep the result that it's setting the result to 0. That's going to keep track of as it runs. And it starts off going from start to max. It figures out how much work to put on each thread, this strange increment calculation where it's basically saying, look, there's some value each, that's how much work we want to put on each thread, but we want to make sure that actually each plus val doesn't go over the final threshold value that we're trying to get to, so it first checks that to figure out what the actual increment should be. And then it calls off to that do partial sum function I mentioned earlier, but now it's spawning off a thread to do that work. So the only interesting thing here perhaps is that middle part, that middle line where it does thread spawn and it has a closure expression. So if you don't know Rust, then those two vertical bars there introduces it's a lambda expression. So if you know C++, just imagine I have a pair of square brackets and a pair of parens there instead of the two vertical bars. In any case, spawning off a thread that just does the partial sum and stores the value in the result. And then after it spawns off that thread, it increments the start so that the next thread that gets spawned will have an updated start value. After it spawns off all the threads, it waits for all of them and then reports its result. So the main reason I wrote the code like this is because I wanted to make it look as close as possible to what the C++ code looks like. Because I wanted to show you that so we could compare the two and benchmark the two together. So this is the C++ code. If you know C++, you might or might not agree with how I've written this. Like I said, this is my first lambda expression was in this slide. It was great because I got to make this code so much smaller than it was before. But it's the same thing over again. We have a vector of threads. We spawn off each one, keeping track of where we want to start and how much work to do in the thread. But it's the same thing where we're just spawning off that thread that's going to do the partial sum and accumulate the result. After we spawn off all the threads, we wait for all of them to report the result. OK, so let's try the C++ code. Let's get some timings. So we run. And I'm a good programmer, so I print out the actual result you computed each time. So I did 4 runs and got the timings. And it's an average of 1 second on my laptop. About 1 second. OK, so what happens when you use 4 threads instead of 1 thread? Well, when you do that, same result. That's good. And it's about a quarter of the time, a little bit more than a quarter of the time. But it's still pretty close. That's great. That means you get C++, we're getting a good amount of speed up per thread. But just to be sure that I couldn't maybe get some more speed up on this laptop, I went to 1,000 threads. Let's see if we get more speed up that way. And the answer here is, nope, you don't get more speed up, but we do get something. We get an invalid result, which means that all of these numbers are bogus because my code doesn't work. My code is broken, so we shouldn't be reporting these timings at all. And what's the problem? The problem is there's a data race. There was a data race in my C++ code. When I showed you that closure expression, there was a little hidden ampersand there that I needed to have because that's the way to say, look, when you have free variables in here, I want them to actually be treated as things I'm referencing by reference so that I can actually do an update of them in this thing where I'm doing result plus equals there to accumulate the values I'm getting. So this is a data race. Each thread is going to be racing to read from and write to that result variable. And that's the very definition of a data race. And so you get undefined behavior. And so what about the Rust version? I made all these claims earlier that you can't have data races. So I basically showed exactly the same code for Rust. What happens here? The answer is that this code does not compile. And thus, we don't have timings for it because the code does not compile. Instead, with Rust 2015, you get this error message that says, you can't do this code the way you wrote it because you're spawning off this thread that has a closure. And that closure might outlive the value you're borrowing. You're borrowing this result value implicitly. And it might outlive it, and so that's not going to work. So what's the issue here? Well, OK. Oh, wait, one more thing about that version, though. It does suggest something. It says, if you use the move keyword before the closure, that'll change things so that you get transfer of ownership. So the next version we try, I'm a person who's all about compiler. When the compiler gives me a suggestion, I just dive right in. Let's try using that suggestion, see if it fixes everything. So this is version 1, because our array indexes start at 0, so the previous thing was version 0. So let's try doing exactly that thing. OK, the great thing is that this code compiles. All I did was add that move keyword, and it compiles now. So we can go to the playpen and run it, but I'll just go ahead and show you what happens. 4 runs, 1 thread. What are the timings we get? Oh, shoot. So what went wrong here? So obviously something's terribly wrong here because the results are definitely wrong. And what's the problem? Well, the joke here is that there's this phenomenon that people often refer to with these strongly typed languages like ML and Haskell and Rust too. This phenomenon of, once I finish wrestling with the compiler, the code magically always works. Isn't it great? But that didn't happen to us this time. So yeah, Rust is not going to prove your code correct. Sorry. But what did go wrong here? The issue is that move keyword we added meant that we were making copies of the values that we had referred to in our free variables. The free variables of this lambda expression are the start integer, the increment amount, incr, and result as well. So it's we're putting a local copy of result into that lambda expression, which then gets updated locally, which is great for that lambda expression, great for that closure, but the original code, the original result that we are trying to accumulate into doesn't get updated at all. So that's the problem here. That's the problem with v1. So that's the sort of way I'm going to introduce ownership, is by talking about that example, is that is this idea of ownership where in Rust you have a notion that every value that's somewhere has an owner. Some of them might be values that can be copied freely. Those integers I talked about could be copied freely between entities, but other things like vectors can't be copied. So here's some examples of Rust types, just to give you an idea of the syntax of the language, a little bit higher level. We have generic types just like C++ and like Haskell and ML and many other modern typed languages. And like C++, we actually implement our generic types by monomorphization. We'll make separate copies of the code for each type that you instantiate at. So that's unlike ML and unlike Haskell. That's because we want to maximize our efficiency in cases like this. So examples of types are things like vectors or strings. So you saw in the very first talk the example of a string where things are being moved from place to place, and this distinction between copying a string versus moving it. In Rust, everything's moved except for really basic data. So vec is moved because it's something that allocates storage. That's this thing you're putting stuff into, the representation of the collection. And likewise, a string is something that's moved. It allocates a buffer and has the buffer of characters. And when you transfer from place to place, it gets moved. It keeps ownership of that buffer as you go. But then there's things that are copyable. 32-bit integers, they're copyable. They can be freely copied. Characters, Unicode characters, they're freely copyable. And then there's these interesting cases like arrays, where if you have an array of copyable things, that's what the syntax here is for this square brackets thing. That's a length n array of t's. If the t is copy, then that array is copy. And this is a tuple over here, a tuple of 3 parts. If those 3 t's are copyable, then the whole tuple is copyable. Okay, this idea of ownership is really important in Rust. It enables a number of things. It enables us to use RAII style destructors. It enables us to ensure there's no dangling pointers, and actually is the basis for us to ensure there's no data races, which, these are all great things for removing large classes of bugs that encounter real code in practice. And the way I sort of like to summarize this is that there's a question that it forces you to ask whenever you're designing an API. It forces you to ask yourself, hey, when I'm transferring this value in, do I need to actually take ownership? Do I need to actually take that on myself and then be responsible for cleaning up after this data type? Or would it suffice just to have temporary access to the data? I don't actually need ownership of it myself. And the interesting part, I think, about this question is that I think good developers already ask this in any language in practice if they care about performance. It's just that in Rust, you're forced to actually encode it explicitly as part of the function signature, and we check it. Okay, so there's more Rust types. In particular, we let you have references to data. There's 2 kinds of references, ampersand mute t and ampersand t. There's also unsafe pointers, which are star t. That's more like the kind of pointer you have in C and C++. Plus, there's a whole bunch of library reference types, box, cow, RC, others. We aren't going to need to talk about those today. So with that in mind, that's enough to move us to version 2 of our program. So here, we're going to do the same thing we did with version 1 in terms of using a move closure. But now we're going to try to actually borrow that result pointer. So we're going to borrow a pointer result and then move that into the closures. So this way, we avoid moving result into each closure, because that was what caused us to fail to actually update the thing that we wanted to update. Here instead, we're going to borrow result and then move that borrow into the closure. And when you try to do this, you would then get a compiler error. In this case, we get the error, at least in Rust 2015, that the result does not live long enough. You're attempting to make this borrow of something, and it's warning you ahead of time. That result is stack allocated. And yet you're passing it to a thread that has to live for the static lifetime. So borrows can't outlive borrows can't outlive the owners of their values that they're borrowing. And this thread spawn function creates a thread that can outlive the stack frame. More generally, it can outlive the whole thread that has spawned it. And that might lead you to the question, well, does every thread have to do this? Do all threads actually terminate at arbitrary times in the program's lifecycle? And the answer is no. In fact, there's alternative threading APIs that will ensure that your threads follow a tree structure where one thread will spawn off other threads, and then they all have to finish before this thread will hand back control in the stack frame. And so in fact, that leads me to then discuss rather than try to put all possible threading APIs into the standard library, in Rust we have this community that's built up this curated set of crates. Our crates is, crate is our word in Rust for libraries. So we have this set of crates online called crates.io, and Cargo is our tool for interacting with that system. So when you design code in Rust, you are free to grab code from crates.io and upload your code to crates.io if you want to share your library with the world. And there's two examples of libraries that I'm going to give a special shout out to because they're all about parallelism. There's Rayon, which is designed by Nico Matsakis, who's one of my colleagues at Mozilla, who is actually the technical lead on the Rust project. And this is a library that's focused on work stealing based parallelism. Who here has heard of Silk? C-I-L-K. Anyone? No, that project's pretty dead. Okay. Who here has heard of work stealing? Okay, so work stealing is a method of thread scheduling where the basic idea is that instead of trying to decide ahead of time, hey, let's have 4 threads and distribute all the work evenly amongst them, what you can do instead is say, look, we've got a pool of threads and we got some amount of work, and we're going to start off work on all the threads at once. And then if one thread finishes what it's working on, it can go and try to grab pieces of work from other threads while they're busily trying to do part of the task they're working on. That's the basic idea. Rayon is all about enabling that kind of programming. But another library that I want to mention is Crossbeam. It's another parallelism library has been developed by Aaron Turon, who's actually the project lead for the Rust project at Mozilla. And he's also a colleague of mine from many, many years ago. So we're going to use Crossbeam to make version 3 because we're going to try to implement this notion of having a relationship between our threads where one parent thread is always going to outlive the threads that it spawns off. We're going to try to make a use of that idea that you don't have to always have your threads dying at arbitrary times. So here's version 3 of our program. And this one, we actually use Crossbeam to create what's called a scope. That's the very first line up here. It creates a scope, and within that scope, we're allowed to refer to things that are outside the scope freely. In particular, we're allowed to refer to that result variable at the very top. The reason this is important is because within the scope, down here, we see the scope spawn. We get to spawn off threads, and we have a guarantee that all the threads that you spawn off within a given scope have to finish before the scope itself, before the closure that we're invoking here at the outermost level returns. I'm explicitly invoking the join method here just for by analogy with my previous slides. But in fact, if I left out these bottom lines here with these joins, the API for Crossbeam would actually enforce that. It would force them all to join itself. So I could have left those lines out and gotten the same behavior here. Okay, the whole point is to ensure that we know that all these threads finish, that we spawned off, before we allow you to return from the creation of that scope object, which means that we know these threads can safely reference that result variable that's on the stack frame. So maybe this fixes everything. The answer is no, it doesn't. We still haven't fixed it. And the reason we haven't fixed it is because Rust has another rule. Rust has another rule that says you can't actually borrow something more than once at a time mutably. If you do what's called a shared borrow, where you only have read access, you're free to go ahead and borrow that as many times as you want and have as many aliases as you want. But if you borrow something mutably, there's a rule that says that means that that person that's doing that borrow has exclusive access to the data that's being borrowed. Of special note here, by exclusive access, the borrower here, like result pointer, borrows result mutably. Even the owner of result, while this mutable borrow is around, even the owner of result doesn't have mutable access to it. It's given up the ability to mutate result and handed that capability off to whoever has result pointer. So the reason that we have these multiple reference types between the shared reference ampersand and the mutable reference ampersand mute is to distinguish between these two kinds of access. And this enables us to have safe parallel APIs in Rust. So the basic idea is there's 3 kinds of types you need to know about. If you just see T by itself, this means ownership. If you transfer a T from one place to another, it means you're transferring ownership. You don't have to say standard move the way we saw in that very first talk. It just happens automatically, which means whatever performance benefits you may or may not expect from that, you get it for free just by moving stuff around. Then there's these other 2 kinds of types that you see a lot, where you see exclusive access with ampersand mute T, which means I have mutable access. And the reason I'm putting that in quotes there is because it really means you have exclusive access. It's a stronger condition than just being able to mutate. It means that you know no one else is going to be able to get that kind of access either. No one else can read or write it. And then there's this shared access thing, ampersand T, which is read only. And I have that in quotes too because there's tricks you can use to get the ability to mutate something that's behind an ampersand T Like you can put in certain types, like an atomic integer that allows you to atomically update something in place. So it's read-only, plus it lets you get mutable access to certain kinds of data types that will be explicit in the source code. But the real point is that it just means it's shared. And the only thing you know when you say &T is that you have read access, and some other people might also have that same ability to access, and you can't predict who they are. So this is me just saying the same thing over again. Exclusive access means you do not allow simultaneous mutable borrows of unsynchronized data. There's like 3 important words there: simultaneous, mutable, and unsynchronized. Oh, geez. Sorry. That's actually my reminder to telling me that I have to leave to go to a meeting. But I'll try to finish the talk. OK, so this rule is usually enforced in Rust via static analysis in the compiler itself. But also we have some library types that enforce it via dynamic checks within the libraries. So all right, I give you sort of this big picture here of all these problems in the code, and then show this final example that had this issue with attempting to take a mutable borrow and having simultaneous mutable borrows of that same result value. And that was the heart of the problem we saw in C++ as well. And in both these languages, you can eliminate this data race rather easily. The common approach is to actually wrap a mutex around the result. And that way, then, whoever updates it has to first grab the mutex, and that ensures no other thread gets access to it. That's one way to do it, and that's a very common approach. Better still, maybe you could use a special atomic operation. All we're doing is updating a variable, integer value here. It's a 64-bit integer, but if we're on a 64-bit platform, we should be able to do compare and swap, or fetch and add, or some other instruction-level atomic operation that'll ensure that this access is synchronized, the update is synchronized, and that other threads will be forced to sort of coordinate with it properly. And maybe better still than that, we don't need to actually take simultaneous mutable borrows of the same result variable. We're only creating, what, 4 threads, maybe 1,000 threads? Guess what? We could allocate state for each one of those threads and let them write into their final destination for their result when each of them finishes. And then when all threads finish, just sum up those 1,000 values, or 4 values, depending on how many threads you make. So there's lots of ways to solve this problem. And you can do it in C++ and Rust. My point isn't to say you can't express this in C++. You can very cleanly. But we didn't think about it, or at least I didn't think about it when I first wrote the code in C++. Rust forces you to resolve this bug in some way. And C++ doesn't force you. It allows silent, scheduler-dependent failure. You may have noticed we didn't see the bug when we ran with 1 thread or 4 threads. Even when we ran with 1,000 threads, I only saw the bug 1 out of the 4 times that I showed you. Guess what? I had to redo that experiment a couple times to actually see the event occur. So it's something where these bugs are very subtle and hard to predict. So here's version 4 of the code. I actually went back using standard thread spawn here because we actually don't need to use cross-beam scope thread abstraction. It's fine here to use the standard thread because one nice thing about Rust's standard thread API is that each closure for standard thread, it can return a result via the handle that you've created. So here, when we do standard thread spawn, we pass it a closure that returns the result of doing the partial sum. And then that result will be stored in the handle for the thread when the thread returns. And that way, now in this for loop down here is where we actually update the result variable. So now we're in a case where this final loop for the threads, when it joins all the threads, it's actually significant that we look at the value that's returned from the join and stash it away. Before we were just discarding the result of the join because there was no information in it. Okay. So yeah. So in case you're curious, yeah, I did the timings for Rust as well. For some reason, it's slightly faster than C++ code. I can't explain why. So there's other cool stuff in the language that we have to leverage these concepts that I've outlined here. We have set and sync traits. That's the way we actually let user data types encode properties about whether a data type can be sent from one thread to another or whether a reference to that data can be sent from one thread to another. There's a distinction here that's subtle and worth looking into. We have lifetimes, our way of actually expressing that you have a reference that outlives another reference or a reference that has to live at least as long as some other piece of data. That's encoded explicitly in Rust via the concept of a lifetime, which I didn't show you any examples of here because I only had very limited time. We allow you to do object orientation. You can write object-oriented code if you want to, but I can't explain how that works. It's different. It's a little different than C++. That's all I'll say. And we have unboxed closures, which or I shouldn't say a lot of languages, but it's unusual to have unboxed closures, I guess. In a language that has closures, usually that means you've garbage collected them in some way, and they're always heap allocated. For us, you can have closures that are stack allocated and ensure that they always finish before they have to return from the stack frame they're allocated on. And we have FFI interop. If you need to interoperate with foreign code, we've got a great interface for that. C++ is the one problem area here because we don't have an ABI that we can guarantee for C++. And I don't know what the plan is personally about this. I should know, but I don't. It's a problem we need to solve. But for now, you have to use C as your base language to interoperate. But a lot of languages resort to C in this case. We have a growing community. I alluded to this before. I've put links to the various conferences that we hold. In particular, RustFest is the EU-based conference that you should look into if you're curious about this. And there's the meetup in Paris. If you actually live here in Paris, we have our Rust Paris meetup. I just recently scheduled, after months of failing to do so, I finally scheduled a meetup for now early November. Who here RSVP'd to the meetup I scheduled yesterday? Okay. Well, I wasn't sure because so many of you said you programmed in Rust already. Doesn't matter. I had to reschedule it because it turned out that the time I chose conflicted with the WebAssembly meetup, and so that was clearly a problem there in terms of an overlap in the communities. Okay. And I want to finally just mention this idea about Rust where, some people thought the project was largely about trying to get C++ programmers to program safely. What we've discovered is a huge part of our community is made up of Rubyists and Pythonistas? I'm not sure, who said, you know what? I was programming these scripting languages, but I wanted to learn more, and this Rust thing seemed cool, and now they've learned so much about systems programming that they got here via Rust. C++ and C scared them. They were worried about the segmentation faults. Rust gave them a path to learn more. And the best way to summarize this is that someone who says programming in Rust has made me look at C++ in a whole new light. That's a nice way of saying I think in horror about all the C++ code I wrote back before I learned Rust. Okay, that's all.
Do you have time to take one question?
I have, yeah, sure. I mean, I'm already late for this meeting at this point. Sure.
Okay, one question. Who's got a burning question? Oh, you might be saved.
All right.
Okay, well, thanks so much, Felix. That was great.